This lesson deals with an analysis of a Motorola 1530 op-amp. You can find these notes in the ECE302 ebook in Chapter 6, starting on page 23. In our last video, we began to do the four-step analysis procedure of a Motorola op-amp that looks like this. We got through steps 1 and 2. Now do step 3, which is to find the AC results, and we're also going to find some of our DC results along the way or reaffirm what we found before. 2 videos back where we found the gain of a two-stage differential amplifier with current source biasing, we found that the output had a DC level of 4.519 volts and had an AC signal that was based on the difference of the two input signals times a gain of 1061. That's now connecting up to transistor 8, which is acting actually as a emitter follower. And let's go back to the schematic. We're feeding that point into here, and we've got a 6K resistor, and we've got all of this other stuff down here. Well, that stuff is going to be something added to 6K of something bigger than 6K total. I don't know the value yet, although I can solve for it. I want to show that as long as this is at least 6,000, then we can neglect the loading effects of this interconnection right here. Let's find the DC voltage here. We're assuming this is about 0.7. Again, that's just an approximation. So let's subtract 0.7 from the 4.519, and we get 3.819 volts. I mentioned last time that we're doing a level shifting. We're starting out with this voltage and eventually shifting it to approximately 0. Let's find the AC results. We found the value of R pi last time for transistor 8. It was 929 ohms. And then between the collector and the emitter, we have a current source of beta FIB, where IB is our phasor current for the base of transistor 8. And then we've got this equivalent resistance here, which is at least 6,000 ohms in value. Let's solve for the AC results here, and we'll add it to our DC results. The current coming in is going to be the voltage here, which is 1061 times the difference of our input signals, divided by the total resistance. So we see 929 ohms here, and then we've got I sub B and 50 I sub B flowing into R equivalent. We're going to multiply R equivalent by 51. This is our equations from the emitter follower of Chapter 5. The output voltage here is going to be equal to I sub B8 times 50 I sub B8 times R equivalent. 51 times I sub B times R equivalent. R equivalent is at least 6,000. If you multiply 6,000 times 51, you get 306,000. This term here is negligible compared to this. We can throw that away. This cancels with this, and this cancels with this. What we got then is our gain of 1061 times the difference of the two inputs. In other words, this is an emitter follower. It's just passing the voltage here to here AC-wise. But we do have a DC level. We're going to add that to it. Okay, so now we're going to connect to the next section. What we found was the output at Vout 8. Let's go back and look at the schematic, see where we're at. We found the voltage here at a DC level plus an AC level, and that's feeding into a resistor of 6K, and then all the stuff that's here. But what this is over here is a current mirror, and we solved for the current in this transistor previously. Put that in as a model and show the rest of the circuitry here. We've got the 5K resistor, the transistor Q12 and Q13, which are 3 stacked in parallel. We have a diode connected transistor, we call it QD4, and then we have our plus and minus 6 volt power supply. But that current mirror is creating a current of 1.559 milliamps that we had solved for in the last video. This is our circuit that we have left for the op-amp. If you look at this, it looks like a inverting amplifier. We know that the output here DC-wise was about 170 millivolts, again something pretty close to 0, but what about the AC results? Well, if we put a short circuit in for the battery, that's an AC equivalent circuit. We have this as our AC circuit. We have to analyze it. But if this gives me enough gain, then what I've got is an inverting amplifier, and I would expect the voltage here to be minus 30K over 6K times this AC voltage. Because this is not a super high gain amplifier, as we'll see in a little bit, it won't exactly be minus 5, but something in magnitude a little bit smaller, so let's solve for that. I'm going to call this the amplifier inside of the op-amp. I want to find basically a model for it with an input resistance, an output resistance, and a voltage gain. And then use that to put back in here and solve for the actual AC voltage gain and eventually also the output impedance of the op-amp. To analyze this amplifier, we'll need to put in a model for each of the transistors and for this diode connected transistor as a diode. Let's do that. Put in an AC model for the power supplies already. So for transistor 11, between the base and the emitter, I have an R pi 11, and between the collector and emitter, I have a beta FIB 11. From the collector back to ground, I have a 5K resistor. And then we found the R pi of the diode and found that it was 25 ohms. Then we found R pi of Q13 as 422. And then we have beta FIB between the collector and the emitter for transistor 13. And then between the collector and the emitter of transistor 12, we've got a beta FIB. And between the base and the emitter, we've got our pi 12. We found that to be 401 last time. And here we also have that our collector is grounded. I'm going to apply a test voltage here, find the output voltage. I want to find the input resistance and the output resistance so I can do a model. So for the output voltage, let's go back around the loop this way. So the output voltage is going to be equal to minus this drop minus this drop. This drop is equal to IB12 times R pi 12, which is 401. And then the drop across here is going to be the current times the resistance. But this current is equal to 50 IB11 plus IB12 times 5K. And again, we're coming this way, so we're getting minus signs. Let's combine the IB12s together. I've got 401, and I've got 5,000. So 5,401 times IB12. And I've got 5,000 times 50 times IB11. Again, two minus signs. So I have V out in terms of IB12 and IB11. I'll need a few more equations to eliminate those two unknowns. Let's go on this end here. The rise in voltage is V test. The drop is equal to IB11 times 1.27K, R pi 11, plus the drop across here, which these two in parallel is a little smaller than 25. It's 23.6. And the current that's coming in here is IB11 and 50 IB11. So 51 IB11. Can combine these two. I get 2,474 times IB11. I've got V test in terms of IB11. I've got V out in terms of IB11, but I've got an IB12 in there. So let's see if we can chip away this and get this in terms of IB11. If you go over here, the current that's coming into this node is IB12 and 50 IB12, so 51 IB12, and what's leaving is 50 IB13. IB12 is related to IB13 by 50 divided by 51, or 0.98. I found something for IB12 in terms of now IB13. Let's relate IB13 back to IB11. IB13 is the current in this resistor, and the current that's entering here is current divided between these two. The current that's entering is 51 IB11, and then if you want the current in this resistor, we take the other resistor over the sum of the two. The formula we derived in ECE302 for a resistive current divider when two things are in parallel. Go back to IB12. It's 0.98 times IB13, but IB13 is IB11 times 2.852. Product of these two is a little bit smaller than this. It's 2.795. Go back to V out. It's equal to minus IB12, but IB12 is equal to IB11 times 2.795. Multiply that by 5,401, and then minus IB11 times 250K. All that combined together is a minus 265,000 times IB11. That's what V out is, but V test is equal to IB11 times 2,474. These cancel with each other. You get a gain of minus 107.1. What's the resistance looking in here? To find the input resistance, we need to find the ratio of V test to IB11, and we already got that up here. V test was equal to IB11 times 2.474K. Well, the ratio of V test to IB11 is just that. So our input resistance looking into our amplifier part of this subcircuit of the op-amp. To complete our model of the amplifier, we need to find the output resistance, and we'll do that by setting the independent source equal to 0. Then apply a V test here and measure an I test, and the ratio of these two would be the resistance looking back in. I sub t here is equal to the current that's entering, that equals the current that's leaving, which is 50 IB13, plus the current that's entering in this direction, which is a minus 51 times IB12. We've got I test in terms of IB12 and 13. Let's take a look at what V test is. Let's go around the loop this way. We've got a drop across here and a drop across here. The rise in voltage is V test. The drop is equal to IB12 times R pi 12, which is 401, but that's a minus sign. And another minus sign times 5K, and the current that's in here is 50 IB11 plus IB12. Let's combine the IB12s, and so I've got two minus signs here, so I'll get those together, and I got 5,401, and then I've got 5K times 50, which is 250K. Same equation we had on the previous page, but for a different part of the derivation. I've got this V test here in terms of IB12 and IB11. I've got this in terms of 13 and 12. Let's get something in terms of IB13. I'm going to again use this current divider. Current that's entering here is 51 IB11, and that's going to current divide between these two resistors. So we'll take the other resistor, if we want the current in this one, over the sum of the two. That's again our resistive current divider from 201. If you multiply all this out, you get 2.852 times IB11, like we did before. You have IB13 in terms of IB11. How is 11 and 13 related? Well, let's go around the loop here. The rise in voltage is 0. The drop is going to be IB11 times 1.27K plus the drop across here, which is equal to IB13 times RPi13, or 422. I know that IB13 is 2.852 times IB11, so I'm going to substitute that in here. And I'll get that 0 is equal to something times IB11 plus something else times IB11. And the only number that works here is 0. IB11 is 0. That means that IB13 is also 0. I can go back to these equations on top here, and this is going to be 0. I've got that I test is equal to minus 51 IB12, and V test is going to be equal to, because this is 0 here also, is minus IB12 times 5,401. Take the ratio of these two, and the IB12s drop out with the minus sign, and I get 5,401 divided by 51, or 106 ohms. I can model my amplifier. It's going to have some resistive feedback around it. That's inside my op amp. I have an input resistance of 2.474K, an output resistance of 106 ohms, and a voltage gain from here to here. And I'm going to show it this way like an inverting amplifier. I'll define this as V sub x, and then I'll make this a positive number here of 107.1 times V sub x. Let's now put this together with the resistive feedback around it. If we go back to page 24, we can now replace the amplifier with our model, and we had resistive feedback of 30K and an input resistor of 6K. And if this was a perfect amplifier, we would expect that the output voltage would be equal to minus 30K over 6K, or minus 5 times the input. But because this isn't super large, and likewise this isn't an open circuit and this isn't a short circuit, we're going to see the gain from here to here in magnitude probably smaller than 5. Let's analyze the circuit using some of our techniques that we had in ECE302. We had an inspection algorithm. I'm going to use that to solve this particular problem. You can find this in the ECE302 ebook in chapter 4 on pages 7 to 8, which talks about analyzing controlled sources. I have two node voltages here, one here and one here. I'm going to call those 1 and 2. Do a source transformation. Take V out 8, the AC part of it, divided by 6K. That's a current source in parallel with 6K and parallel with this 2.474K. Let's go do a source transformation over here. Take the voltage divided by the resistance, and that'll be a current source pointing in the direction of where the plus sign was, and in parallel with that would be 106 ohms. Node voltage 1 is equal to minus V sub x, and node voltage 2 was equal to V out. Our inspection algorithm was to form a 2x2 matrix, where in row 1, column 1, we're going to add up all of the admittances hooked up to node 1. That's 1 over 6K, 1 over 2.474K, and 1 over 30K. Between nodes 1 and 2, there's a 30K resistor, so we're going to subtract 1 over 30K. Current that's entering this node goes into this location in the left-hand side of the equation, first row, first column, and that's V out 8 divided by 6K. At node 2, we're going to sum up all the admittances hooked up here, so it's 1 over 30K and 1 over 106 ohms. Between nodes 2 and 1, I've got a 30K resistor, so minus 1 over 30K. And then the current sources that are entering this node are 107.1 V sub x divided by 106. So I have two unknowns, V1 and V2, but I also have another unknown, V sub x. But if you look up on top, V sub x is a minus V1. If you substitute in here a minus V1, take this ratio, you're going to get a minus 101 times V1. When you put that on the other side of the equation, it's going to go into this column because there's a V1 here. And that'll become a plus 101 added to this reciprocal, which is a minus 33.3 micro. I did this summation and got 604.2 micro. This was a minus 33.3 micro, same number here. Bringing this over here is this one. The sum of these reciprocals is 9.467 milli. Let's now solve for the node voltage V2, which is our V out. We're going to use Kramer's rule to do that. Solving for V2, we're going to take a ratio of two determinants. The denominator determinant is our matrix here, and then in the numerator we're going to take this same matrix, but we're going to replace column 2 by the left-hand side of the equation because we're solving for V2. I'm going to put this over here. This times this is 0, and then minus this times this is this term, and then this times this is 5.72 micro, minus this times this is a plus 33.63 micro. Doing the math here, I get a minus 4.278 times V out 8, and that's equal to the V out of our op amp. We were expecting a gain of minus 5, but we're getting a gain of minus 4.278. That's going to multiply that differential gain that was coming in of 1,061. V out is equal to minus 4.278 times V out 8, which was 1,061 times the input difference between 2 and 1. So you multiply these two here, I get a minus 4,539. Let's get rid of this minus sign by bringing it through here. I've got 4,539 times V in 1 minus V in 2. Now we'd also like to know what is the output impedance of the overall op amp, and we can find that with our amplifier by setting the input that's equal to here to 0, which is really setting the original differential voltage is equal to 0 because that would come through with a gain of 0. And then look back in here and find the resistance. Put a test voltage and a test current. Their ratio is R out. Applying a voltage V test here, I'm going to have a voltage V sub x here with a voltage divider around this loop, which is going to be with this parallel combination of 6K with 2.474K, which is 1.752K, voltage divided with 30K. Because the plus sign is here and the minus sign is here, we're going to have a minus sign with this voltage divider. We get minus 55.18 milli times V sub test. If V sub x in terms of V test, now what is I test equal to? Well, it's equal to this current plus this current. Now this current is going to be equal to the voltage across this resistor, which is V test, minus 107.1 V sub x divided by 106. And of course the current in here is just going to be V test divided by the total resistance of 30K plus 1.752K. This divided by this is 9.434 milli times V sub t. This ratio is 1.01 times V sub x with a minus sign, and then the reciprocal of this is 31.49 micro times V sub test. So let's put these two together. That gives me 9.465 milli times V sub test. And then I've got V sub x times 1.01, but V sub x is equal to minus 55.18 milli times V test. I can add these two together, get 65.197 milli times V sub test. Now take this, bring it on this side of the equation, take the reciprocal of this on our side of the equation, and now get the output resistance of the op amp, which is 15.33 ohms. Step 4 of our algorithm, we can add all the results together. So here's our op amp that we've been analyzing. And we found that it had an output voltage, it had a DC component and an AC component. This is targeted to 0 because we're making approximations. We got 0.17 volts, but in reality it's something close to 0. We've got the output is something times the difference of the input, and that difference is that we call the differential mode gain of 4,539. We found that the input resistance to the differential amplifier in a previous video is 5.28K, had a common resistance of infinity, and we just found that the output resistance was 15.33. You can construct an equivalent circuit for this if you want to show a differential input resistance, a voltage-controlled voltage source with a series output resistance. I've drawn here a symbol of an op amp and labeling this as the MC1530, where we've got a positive input and a negative input, and relative to this we get a positive gain, plus and a minus power supply and an output pin. Pin 3 is actually the ground connection. There's 4 more terminals here on this IC, and they're labeled lag compensation and lead compensation. What this is referring to is that if you put resistive feedback around this op amp, it may become unstable. And that's because these transistors and diodes have some capacitance, and when you put feedback around it, you can take the poles that are here, which are actually in the left half plane, and force them into the right half plane, and create an oscillator or a lockup condition. We need to take a look at next is what is the capacitance associated with a transistor or a diode, and that's the material of Chapter 10. And this is the analysis of an MC1530 Motorola op amp.